We are going to finish up section 6.2 here, starting on page 369 with the take note combining quotient radicals. Same idea here as it was with multiplying. As long as our indexes are the same, we can take and write it all as one radical with our radicands divided. So if we look here in A, our index for both of these are 2. So since they're the same, we can write it as one radical. 18x to the 5th divided by 2x cubed. We can reduce here. 18 divided by 2 is 9. X to the 5th divided by x cubed is x squared. Here we subtract our exponents. It's like if I had x to the 5th divided by x cubed. Those cancel out and I'm left with x squared. Now, that's all still inside my radical. All I did was reduce this fraction. Now, in order to simplify this further, I can take the square root of 9, which is 3, and the square root of x squared gives me just an x. And here, again, I know I don't need the absolute value bars because this is odd, so it had to have already been positive. Same thing here, had to have already been positive, so my x is going to be positive here. If you want to put them there, you certainly can, but you don't need them. 3x is what we're looking for. In B, same idea, it's just a different index, but they're the same. So same index, we can check that off. I can write it as 162y to the 5th power divided by 3y squared. I write it as one radical because now that I have it as one radical, I can reduce. When I take 162 and divide by 3, I get 54. So it's 54, and again I'm going to subtract my exponents here, y cubed inside my radical. 54, I can break down, is 27 times 2, 3 times 9, and 3 times 3. So here, I get 2 times 3 times 3 times 3, y cubed. So again, if you didn't recognize that right here we have a perfect cube, you can break it down further. If you did, you can take the cube root of 27 and get 3. The 2 stays inside of our radical, and y cubed divided by 3 gives me just 1y, remainder none. If you didn't see that right away though, we can write it as our prime factors. I have a group of 3 3's, a group of 3 y's, and everything that's not in a group goes inside my radical. So we reduce them the same way that we did yesterday in the first half of the notes. We just divide first instead of multiply first. Now, go ahead and pause here and try this if you'd like. Since they're both square roots, they don't have numbers there, which means we know that it's 2. We take the square root and write it as one fraction inside, because when we do that, we can reduce. 50 divided by 2 is 25. X to the 6th minus x to the divided by x to the 4th, we subtract exponents and get x squared. And that's still inside the square root. When we take the square root of 25 here, we get 5. And when I take the square root of x squared, I just get x. Remember, here's a 2. We reduce. Here, though, because I had even, and odd, I need my absolute values, because at any point along the way here, this could have been a negative number, but we want the positive value, which means we need just the positive. So, because our negative won't go away, we know that here it could have been positive or negative, here it could have been positive or negative, because when we take it to an even power, it's positive. So inside our radicals, we can't tell if our x originally was positive or negative. So we have to take the absolute value of it here. Rationalizing the denominator is rewriting an expression so that there are no radicals in any denominator or no denominators in any radical. So that pretty much sounds very similar, and what they're telling us, guys, is that if we have it written as 1, we can't have any denominator in our radical. If it's written as 2 radicals, there can't be any radicals left in the denominator. So it's really just telling us whether we have one fraction or with inside our radical or a fraction of 2 radicals. Either way, there can't be any square roots, cube roots, things like that, radicals in the denominator. And when we rationalize our denominator here, it's a similar concept kind of to what we did when we rationalized when we got rid of the complex numbers in our denominators, when we used our complex conjugate. Here's going to be the similar idea. So if we look, we're trying to get our denominator so it's not inside a square root anymore. We can rewrite this, since it's cubed for the whole fraction, as 2 separate radicals, as long as we keep the same index. Now, we know that because our index is a 3, we need groups of 3 in order to take them out of there. So what I'm going to do is I'm going to multiply by the cubed root top and bottom, because whatever I do to one part of my fraction, I have to do the other. And I'm going to get complete sets. So here I have 112. So I'm going to multiply by 2 more, because again, I need sets of 3. So here I have 1, 2, 3, which matches. Here I have 2 y's. I need 1 more to get a full set of 3. Here I have 1 z. I need 2 more in order to get a complete set of 3. I'm going to do the same thing on the top. Now, I can multiply across the top, and since they're the same index, I can write them as 1. 5 times 12 squared is 720. X squared, I don't have any over here. Y and z squared in my numerator. In my denominator, I have 112 here and 2 there, which gives me a total of 3. So I have one group of 12s. I have 2 y's and a third y, so I have one group of y's because I need 3 of them. 1 z and 2 z's gives me a total of 3 z's, which gives me one group of z's. Now, the only thing left is to reduce if we can. 720 we've done before, but that's going to be 2 times 360, which is 2 times 180, which is 2 times 90, which is 3 times 30, which is 3 times 10, which is 2 times 5. Okay, however you want to break it down there, doesn't matter. What does matter is that when it comes to groups of 3, I have a group of 3 2's, and I can take that out. So what I have here is 2, and inside I have 3 times 3 times 2 times 5, which is 90. 9 times 10, 90. So instead of having this part right here, I'm going to rewrite it as 2 times the cube root of 90. And I still need to bring my variables over. X squared, y, z squared, over 12y, z. Final step here, 2 and 12. I can divide a 2 out of each of them. I get the cubed root of 90, x squared, y, z squared, over 6y, z. Okay, feel free to go ahead and give this one a try. Okay, so I already have them written as separate pieces, which is helpful. Now, I need to multiply by the same thing top and bottom, and I'm trying to get rid of this radical. So what I need is 3 5's to get rid of my 5, and 3 y's to get rid of my y's, because it's 3. Right now, I have 1 5 here and 2 y's. So what I still need to multiply by are 5 times 5, or 5 squared, and y. So I'm going to multiply by the cube root of 5 squared y. And whatever I do to the bottom, I have to also do to the top. Now if I look here, I have 1, 2, 3 5's, and 1, 2, 3 y's. I have a group of 5's and a group of y's. So in my denominator, all I have left is 5y. In my numerator, I'm going to take 7 times 5 squared, which is 25. I'm going to get 175. I have an x and I have a y. Okay, that's going to be our final answer, but if you're not sure, break 175 down into its factors. We have a 7 and a 5 and a 5. Here I don't have a group of 3 of anything, so there's nothing I can take out. So this right here is our final answer. Okay, remember that when we're rationalizing the denominator, we're trying to keep it so that there's no square roots in the denominator or no denominators inside our square root if it's written as one big square root. And we always want to leave our answers that way anytime we're dealing with dividing. Quick recap here for section 6.2. If the nth root of a and the nth root of b are real numbers, then we can rewrite them as the nth root of a times the nth root of b equals the nth root of a times b. We can take our radicands and multiply them together as one radical as long as our indexes are the same. A radical expression can be simplified when the exponent of one factor of the radicand is a multiple of the radical's index. The product of the powers that have the same exponent can be simplified, and the product of radicals that have the same index can be simplified. And that's all I have for section 6.2.